Hi, my name is Bill. Welcome to Probability and Statistics for Everyone. This is video 2.1, a first installment in multiple videos to replace an original video 2. If you haven't seen video 1, my welcome message to the channel, I encourage you to check it out. In this video, we'll begin our exploration into probability and statistics, beginning with a definition that I've come up with to introduce them both while drawing a distinction between them. So let's get started. In the presence of randomness, probability is the science of prediction and model development, while statistics is the science of data description and inference. In video 3, we'll break this definition down into key words and phrases and explore each of them on their own. Here, though, let's begin by considering a hallway with a door to the probability lab on the left and a door to the statistics lab on the right. In the probability lab, they deal with predicting the rates at which random outcomes occur, and then develop mathematical models of those outcomes and those rates. Take, for example, rolling a simple six-sided die. What is the probability of that die landing with a side labeled 5 coming up? Conventionally, that is under the usual assumptions, it's 1/6, under a general model that each of the 6 sides is equally likely to come up. Perhaps a more interesting question would be, what is the probability of that die landing with the number 5 facing the camera? We'll defer that one for now, but it wouldn't be too complicated. As I said, the next thing the probability lab would do would be to develop a mathematical model for the possible outcomes. In equation form, that model would look like this. This equation is called a probability mass function. It says that the probability that the outcome P of x is 1/6 if x equals 1 or 2 or 3 or 4 or 5 or 6, and 0 otherwise. It is always true that in any probability model, the sum of the probabilities of all the possible outcomes equals 1. In graphical form, that model would look like this. In the plot, there is a bar of height 1/6 at each of the values 1 through 6. We turn our attention now to the statistics lab, again by considering an example. Suppose we have a vase which we're told contains some number of plastic chips. We're not told how many, or whether they're black and white, or gray, or colored, or whether they're decorated with numbers, or letters, or spots, or anything, just chips. We're initially told that the assignment is to determine how many chips and what kinds of chips are in the vase. We reach in and pull out a green chip, which is otherwise blank. Next we pull out a yellow chip, and then another green chip. Afterward, what have we learned about the chips in the vase? Well, we've learned there are green and yellow chips, which so far are otherwise plain. So we ask for more information, which leads to a modified, more refined problem statement. We're now told that there are 40 chips in the vase of various colors, that each color has at least 5 chips, and we're directed that we may remove no more than 10 chips. In response, we draw 7 more chips, which yields a total of 4 green ones, 3 yellow ones, and 3 red ones. In many applications of statistics, we deal with evolving knowledge or assumptions about the problem at hand, and a tightening of the objectives of the study. So to receive some initial information about a system, and then have that information clarified or even reversed, is not uncommon. It is the task of the statistician to continually update the body of knowledge about a system and then still draw generalizing conclusions about that system. So what now can we say about the chips remaining in the vase? We were told that there were originally 40 chips, so there are now 30. We know that it has, or at least had, at least 3 different colors of chips. Is there still a 4th color or even 5th color of chips that somehow were not randomly chosen among the first 10 chips we pulled out? Or are all of the remaining chips either green, yellow, or red? More precisely, as an example, what is the probability that there is one more color of chips in the vase, meaning that at least 5 of them are in there, given the 10 chips we just selected? Notice that is a question for the probability lab, but statisticians are asking probability questions all the time. Here, on the table with a black cloth, we could of course simply turn the vase over and count the chips. But in actual applications of statistics, that is impossible or feasible. Consider an example where some new safety feature on a certain make of automobile needs to be evaluated. We might select 10 cars from the manufacturing line, put them through destructive crash tests, and record the results. We could find that some passed completely. Think green chip. We could find that some performed marginally well. Think yellow chip. And we could find that some just completely failed. Think red chip. Turning the vase over would be like destroying all of the cars from the production line to directly measure the safety of the new feature. There would be no cars left to drive, so what would be the point? Getting back to our example of chips in a vase, the best we can do at this point is use our 10 chips already drawn to infer the color of the chips remaining in that vase. We begin by presuming that all of the rest of them are either green or yellow or red. Next, we calculate the rates or proportions at which they showed up on our sample of 10 and use those rates as predicted general rates. So for example, we have P sub G hat, which is our estimate of the rate at which green chips are in the vase. Note, we generally use a hat to indicate estimates. We also have P sub Y hat for yellow chips and P sub R hat for red chips. We then multiply each of those rates by 30 to get our estimates of the number of chips of each color remaining in the vase. With just a single die and a mug, and then with plastic chips in a vase, we've just begun to see how probability and statistics are interrelated but distinct from each other. The science of probability is a purely theoretical endeavor, while statistics is the science that gives probability its grounding in actual applications. We'll continue to explore these two in subsequent videos, so keep coming back.